In the last videotape, we discussed triangles, closed three-sided figures. Today's videotape deals with quadrilaterals, closed four-sided figures. Now, in the last videotape, we learned that the angle sum of a triangle is 180 degrees. For any triangle, the sum of the angles in the triangle, they add up to 180 degrees. In a quadrilateral, it can easily be shown that the sum of the angles of a quadrilateral, any quadrilateral, is 360 degrees. Okay. To show this, simply connect two opposite vertices, and you will see that the quadrilateral breaks into two triangles. Now, the angle sum here is 180 degrees, and here also 180 degrees. Together, we get the 360 degrees for the quadrilateral. If you label this, say, angle 1, angle 2, angle 3, angle 4, angle 5, and angle 6, we know that angles 1, 2, and 3 sum to 180 degrees because we have a triangle. Also, angles 4, 5, and 6 sum to 180 degrees, and adding up these equations, adding the left sides and adding the right sides, we get that angles 1, 2, 3, 4, 5, and 6 add up to 360 degrees. And you will notice that angle 2 is this angle of the quadrilateral, 3 and 4 compose this angle 5 for this vertex here, and angle 6 and 1 give us this angle here. For the four angles of the quadrilateral, they add up to 360 degrees. Okay, so for a triangle, the angle sum is 180 degrees, and for a quadrilateral, a four-sided figure, the angle sum is 360 degrees. Okay, let's look at a small example. Let's say we have a quadrilateral with a right angle in here. That angle is 90 degrees. And let me designate the degree measure of this angle by x. This angle here, let me denote by 2x. And this angle here by x plus 30 degrees. And suppose I ask you to find all the angles in this quadrilateral. Now, since the sum of the angles of a quadrilateral must be 360 degrees, I know that 90 degrees, which is the angle in here, plus 2x, the angle here, plus x, the angle here, plus x plus 30 degrees, the angle there. The four angles must add up to 360 degrees. On the left side here, we have 2x plus x, that's 4x, plus 90 degrees and 30 degrees, that's 120 degrees, equals 360 degrees. Subtracting 120 degrees from both sides, we get 4x equals 240 degrees. Dividing both sides by 4, x comes out to be 60 degrees. If x is 60 degrees, that means that this angle here is 60 degrees. This is x, this is 60 degrees. This angle is 2 times x, 2 times 60, that's 120 degrees. And this angle, which is 60 and 30, of course, is 90 degrees. It looked like a right angle, and it happens to be one as well. Okay, so 90 and 90, 180, and 120 and 60, another 180, adding up to 360 degrees. Okay, now certain quadrilaterals come up a good deal, and we give them special names. Let's start with one of these special quadrilaterals, which we call a parallelogram. A parallelogram is a quadrilateral, okay, in which both pairs of opposite sides are parallel. It looks something like this. Well, something like that. Both pairs of opposite sides are parallel. This side is parallel to this, and this side is parallel to that. Okay, parallelogram. A quadrilateral having both pairs of opposite sides. It's a nice abbreviation. Opposite sides parallel. Quadrilateral having both pairs of opposite sides parallel, hence the name parallelogram. Okay, now there are other possible criteria for a parallelogram. Instead of saying it has both pairs of opposite sides parallel, we could say it has both pairs of opposite sides equal. Both pairs of opposite sides equal in length. Okay, this would also be another way of defining a parallelogram, or we could say it has one pair of opposite sides, both parallel and equal. Okay, if both pairs of opposite sides are equal in length, you can convince yourself that the opposite sides would also have to be parallel. If you fool around with possible drawings, you would come to this realization. If you had one pair of opposite sides, both parallel and equal, okay, then it would also have to be true that the other pair of opposite sides were parallel and equal. Okay, so in any of these conditions, you would have a parallelogram. Other interesting facts about the parallelogram are that in a parallelogram, the opposite angles are equal. In a parallelogram, the opposite angles are equal, and also the diagonals bisect each other. Okay, let me illustrate that for you. If you have a parallelogram, it doesn't look much like a parallelogram. Anyway, use your imagination. This angle is equal to this angle. The opposite angles are equal. This angle equals this angle. When I say the diagonals bisect each other, I mean if you draw in this diagonal and you draw in this diagonal, when this diagonal crosses this one, it cuts this one into two equal portions. It bisects the other diagonal. Similarly, when this diagonal crosses this one, it cuts this diagonal into two equal segments. Okay, now this is not true in general for any old quadrilateral. If you have a quadrilateral like this, here's one diagonal, here's the other. Okay, it is clear that this diagonal does not divide this one into two equal segments. Okay, but if your quadrilateral is a parallelogram, then the diagonals will certainly bisect each other. Okay, if in a parallelogram you are given one of the angles, it is possible to find all the others. Let's say we have a parallelogram. And I tell you that this angle is 70 degrees. And I ask you to find all the remaining angles. Okay, we're going to be using two bits of information here. First of all, we're going to use the fact that the angle sum of a quadrilateral is 360 degrees. And secondly, that in a parallelogram, the opposite angles are equal. Okay, this is a parallelogram. Okay, since it's a parallelogram, the opposite angles are equal. If this angle is 70 degrees, this angle is also 70 degrees. I don't know what the other angles are, but it is clear that they are also equal. So let's denote the angle here by x and the angle here by x. X is the measure in degrees of these angles. Okay, we don't know what they are, but the opposite angles here are going to be equal just the same way the opposite angles there are equal. Now, since it is a quadrilateral, the angle sum is going to be 360 degrees. So 70 degrees plus x plus 70 degrees plus x must be 360 degrees, or 140 degrees plus 2x is 360 degrees. That gives us that 2x is equal to 220 degrees, subtracting 140 from both sides, and x comes out 110 degrees, dividing both sides by 2. So this is 70, this is 70, this is 110, and this is 110. Okay, in a parallelogram, the opposite angles are equal. By the way, it can also be shown that the adjacent angles are supplementary. It has to work out that way. Okay, 70, if let's say this was y and this was y. Y and x have to be equal to 360. Dividing by 2, you can show that x plus y must be 180. That is, the adjacent angles must be supplementary. So knowing that this was 70, this has to be 110. They have to add up to 180. The opposite angles are equal. And once again, the opposite angles are equal. Most of these you have seen before. You haven't thought of them necessarily as parallelograms. The first one is a rectangle. A rectangle can be defined to be a parallelogram that has a right angle in it. Okay? Let this symbol represent a parallelogram. A parallelogram with one right angle. Now you might say, well, I thought rectangles had 4 right angles. Okay. They do. But all you have to show is that you have a parallelogram with one right angle in it. Okay, it's a parallelogram, so the opposite sides, of course, are equal in length here and here. Okay, now if you have one right angle, since it's a parallelogram, the opposite angles are equal. This must also be a right angle. And since the angle sum is 360 degrees, and these are equal as well, these must also be right angles. The only way it can work out. So it's sufficient to say a parallelogram with one right angle, because if you have one right angle, you can easily show that there must be 4 right angles in the parallelogram. The next one, a square. A square is a rectangle that has 2 adjacent sides equal. And you might say, well, I thought a square had 4 sides equal. It does. But all you have to do is show that it's a rectangle and 2 adjacent sides are equal. The fact that it's a rectangle or a parallelogram tells me that the opposite sides are equal. Okay? The fact that adjacent sides are equal as well means that all 4 sides must be equal in length. These are special parallelograms. One more quadrilateral that I want to mention is a trapezoid. It is not a parallelogram. A trapezoid is a quadrilateral having one pair of opposite sides parallel. This. Okay, one pair of opposite sides are parallel. If the other pair were also parallel, you have a parallelogram. If both pairs of opposite sides are parallel, it's a parallelogram. If one pair of opposite sides are parallel, it's a trapezoid. We will always use the most descriptive term. Over here, you could say that a square is a rectangle, but if you're looking at something like this, I prefer you to call it a square rather than a rectangle. You could call this a parallelogram. I prefer you to call it a rectangle. Okay. Similarly, you could think of a parallelogram as being a trapezoid. Okay, but we will, if you have both pairs of opposite sides parallel, we'll call it a parallelogram. One pair, we will call it a trapezoid. Always trying to use the most descriptive term that we can. Okay, now that we have all these names, we'd like to discuss how to find the area and perimeters of these figures. So let's do that right now. Area and perimeter of triangles and quadrilaterals. Okay, first let's discuss the question of perimeter, because that doesn't really need any special handling. The perimeter of a figure represents the distance around the figure. If you would consider a triangle, okay, it's the sum of the lengths of the three sides. It's a measure of the distance around the figure. If you were going to fence off something with this shape, okay, how much fencing would you need? Okay, so for a triangle, if you have three sides, you would simply add up the lengths of the sides. For a quadrilateral, let's say you had something like this, and I told you that this side had length 3, this side had length 4, this side had length 6, this side had length 5. You would not need any special handling here. You would simply add up the lengths of the four sides, and the perimeter would be 3 plus 4 plus 5 plus 6, which comes out to be 7 and 5, that's 12 and 6, 18 units. Okay, so no formulas, just simply make sure you've covered all the sides, go all the way around, start at one point here, say, and go all the way around the figure. 3 plus 5 plus 6 plus 4. Get back to where you started. That's the perimeter. Okay, now let's concentrate on area. Area is a little bit harder. Our basic building block in area problems is a square that has length 1 unit. Each length of each edge is 1 unit. This is 1 by 1. Okay, it's a square. The area of such a square, 1 unit on a side, okay, the area will be called 1 square unit. Okay, from this, we can find the area of many other figures. Let's look at a rectangle. Okay, let's say this rectangle is 2 units by 4 units. You can break this up like so and see that there are 8 of these figures in this rectangle. Since each one of these has area 1 square unit, then it seems natural to call the area of this rectangle 8 square units, since there are 8 of these. Okay, the area here is 8 square units. And you notice that this can be found by taking the length times the width. 2 times 4 to give us the 8 square units. The area of a rectangle is defined to be length times width. L represents the length, W the width. Okay, and the logic you can see, it's how many of these squares you can fit into the rectangle. Okay, you can alternately call this base times height. Instead of length times width, you can call the length here the base. Okay, the side that the rectangle is resting on, and the width here is the height. Okay, so either length times width or base times height for the area of a rectangle. Okay, what would be the area of a rectangle? Dimensions. here's a rectangle, and the dimensions are 2 by 5. The area, base times height, okay, 5 times 2, or 10 square units. Whatever your unit happens to be. In perimeter, okay, it's the distance around the figure. Your perimeter comes out in units, inches, feet, whatever you're dealing with. Okay, it's simply the length, the sum of the lengths of all the sides. So your unit is a unit of length, inches, feet, whatever, 18 units. In area, however, your unit comes out to be square units, square inches, square feet, whatever. Okay, now that we've handled a rectangle, by the way, a square can come under the same categorization. If we have a square, okay, that's has length, the length of each side is 2, and obviously it breaks into 4 of these unit squares, and we can, in the same way we handled the rectangle, we could still say it's base times height. But since the base and the height are both equal to the same quantity, they're both, let's say they're both the length of a side, we can say it's s times s, or s squared. The base is 2, the height is 2. Okay, the base and the height are the same. We can call that the length of a side s. The area is, instead of base times height, s times s, or s squared. In this case, you get 2 times 2, or 4 square units. From the rectangle, we can jump off and figure out the area of a parallelogram. Let's do that over here. Here we have a typical parallelogram. Typical for me, at least. Okay, now we want to figure out the area of this parallelogram. If you were to drop a perpendicular from this vertex here to hit the other side here, to hit the base, you would form a right triangle. It can easily be shown that this triangle happens to be congruent to this triangle here, the one that you would get by dropping a perpendicular from this vertex to the extension of the base here. It's nothing to show that these triangles are similar. You have here parallel lines cut by a transversal, so certainly these angles are equal. Parallel lines cut by a transversal, these angles are equal. They both have right angles, therefore the third angles must be equal as well. And aside from that, you also have the opposite sides of the parallelogram equal. So these two triangles are definitely congruent, which means if you were to cut this one off, pick it up and stick it on here, it would exactly fit in there. Okay, now what does this tell us? We started with this parallelogram. Let me just make sure you see where we started with. We started with this parallelogram. We're interested in finding the area of this parallelogram. What we do is we cut off this triangle, stick it on here, and we see that the area of this parallelogram is exactly equal to the area of this rectangle. Now the area of this rectangle is base times height. Now for the rectangle, the base goes from here to here, and the height is from here to here. Right, this is the rectangle, the base, and the height. Okay, the area of the parallelogram is equal to the area of the rectangle, which I've indicated on the diagram, which is base times height. The base goes from here to here, and the height from here to here. Now looking at the rectangle, at the parallelogram rather, you will notice if this distance is b, this length is b, then this length is also b, from here to here. In other words, the base of the rectangle from here to here is exactly equal to the base of the parallelogram. Because we're using this quantity, and whether we add the triangle on here or we add it on here, it doesn't matter. So from here to here is b, that's the base of the rectangle. From here to here is b, that's the base of the parallelogram. Now the height. The height of the rectangle is this quantity here, this length here. The height of the parallelogram is considered to be this. Okay, when I say the area of a parallelogram is base times height, the base is clear. The height is not the slant height here. This is not h. This is not h. This is a slant height. We mean the perpendicular distance between the parallel sides. Okay, the distance between these parallel sides, okay, measured perpendicularly like this, not the slant height. The area of a parallelogram is therefore base times height. The base is obvious. The height is the perpendicular distance between the sides. Okay, let's look at a simple example. Let's find the area and the perimeter of this parallelogram. Okay, let's say the length of this side is 2. The length of this side is 6. Okay, and the length of this side, well, not the perpendicular distance here is 3. Okay, we have a parallelogram. The length of this side is 2. The length of this side is 6. The perpendicular distance between the sides is 3. And I want both the area and the perimeter. Okay, let's start with the perimeter. The perimeter is the distance around. Well, only 2 of the sides are labeled, but the opposite sides of a parallelogram are equal in length. So if this is 2, this is 2 as well. And if this is 6, this is 6 as well. So we get 2 plus 6 plus 2 plus 6. So the perimeter comes out to be 2 and 6, 8 and 8, 16 units. Oh, by the way, the picture that I just drew is impossible. I was just anxious to give something that looked all right. The 3 could not possibly. You have a right triangle here. The hypotenuse has to be longer than the length of this side. Let me just change this to a 1. Okay, and then everything else will still be accurate. Okay, you can't have the hypotenuse is the longest side in a triangle. Okay, so this is 1, this is 2, this is 6. Now the perimeter is still 2 plus 6 plus 2 plus 6, the distance around. Now let's work out the area. The area is base times height. The base is 6. The height is 1. It's not 6 times 2. It's 1, the perpendicular height. Okay, A is 6 square units. Okay, now from the parallelogram, let's move on and find the area of a triangle. We know the area of a parallelogram is base times height. We're going to use that to find the area of a triangle. Let's look at a triangle, like so. If you were to put right next to this triangle a triangle congruent to it, but positioned like so. Okay, this triangle here is congruent to this one. Okay, it's upside down and turned around, but it's congruent to this one. These two triangles, which are congruent to each other, put together like this, form a parallelogram. Okay, it's not too hard to show that. We have these two triangles together, they form a parallelogram. If the area of a parallelogram is base times height, okay, the area of this parallelogram, height being here, the perpendicular distance between the two parallel sides here, this is the height. For the parallelogram, this is the base. Base for the parallelogram, base and height. If the area of the parallelogram is base times height, then the area of the triangle should be 1/2 of the area of the parallelogram, 1/2 base times height. And you may have seen this formula before. The area of a triangle, 1/2 base times height. Okay, the height in the triangle is called the altitude. An altitude is a line segment from a vertex perpendicular to the opposite side. Okay, and do not feel that the altitude must be within the triangle. If you have a triangle that looks something like this, Okay, now you could find the area of this triangle by saying that this is the base and this is the height. Okay, doing it this way, that's perfectly okay. 1/2 base times height. Okay, but you're not restricted to doing that. You could also find the area of this triangle by calling this the base and this the height. Now the height from this vertex perpendicular to the side here, the altitude here would not be within the triangle, but it would still be the altitude. The altitude is not contained in the triangle, but you can still use it in your calculations. 1/2 base times height this way would come out exactly the same as 1/2 base times height using, say, the other pair over there. So the altitude does not have to be within the triangle. You can still find the area. Okay, let's look at a typical example. Let's say this is the altitude has length 3 and the base here has length 6. Okay, the area is therefore 1/2 base times height, 1/2 6 times 3, 1/2 of 18 or 9 square units. You could have also said 2 into 6 goes 3. 3 times 3 gives you 9 square units. By the way, at this point, we do not have enough information to figure out the perimeter of this triangle. Okay, it is not obvious what the other sides are. We can get the area, but not the perimeter in this problem. Okay, and the last figure I want to give you the formula for area is the trapezoid. And this follows from the triangle that we just worked out. Okay, a trapezoid is a quadrilateral having one pair of opposite sides parallel. From the point of view of making the formula seem a little more logical, I'm going to give you a trapezoid that has a right angle in it, but the formula that I'll give you is perfectly applicable for any trapezoid whatsoever. Okay, let's say that these are right angles. Doesn't have to be that way. This is the example that we're working out. Okay, now, if you were to draw this diagonal in here, you would cut the trapezoid into 2 triangles. Okay, let us call this triangle here, let's say that this has base B1, and the triangle up here, let's say its base is B2. B1 and B2. The height of this triangle is H. Of course, is the same as the height of this triangle, since these sides are parallel and therefore the same distance apart. Okay, so we have 2 triangles. The area of the trapezoid is equal to the area of triangle 1 plus the area of triangle 2. This being triangle 1, this being triangle 2. Now, the area of triangle 1 is, of course, 1/2 base times height, 1/2 B1H, because the base in triangle 1 is B1, and the area of triangle 2 is 1/2 base times height, where the base now is B2. Okay, 1/2 base times height, and